Hello, my name is Savannah Swanson, junior at Washington State University, School of the Environment. Welcome to Kamiak Butte. Kamiak Butte is a national natural landmark located about 15 miles north of Pullman, Washington. It rises above the Palouse farmlands at an elevation of 3,641 feet and appears as a forested island from afar. The creation of Kamiak Butte can be traced back to the formation of the modern Pacific Northwest, beginning about 100 million years ago with the delivery of Superterrane 1 by the Farallon Plate as it moved northeast. The delivery and accretion of the superterrane to the North American Plate led to the formation of a large continental batholith, later known as the Rocky Mountains. At 70 million years, the large Farallon Plate split into the smaller Farallon and Kula plates and began to move north. The larger, less dense North American Plate forced the smaller plates to subduct under it as it continued west. This ultimately led to the delivery of Superterrane 2, formation of the Cascade Mountain Range, and uplift of the Rocky Mountains. By 50 million years, the Kula and Farallon plates began moving more northeast, simultaneously moving the superterranes north to Canada and forming Vancouver Island. The continued subduction of the Farallon Plate led to the formation of the Olympic Peninsula and fueled the volcanoes of the Cascades. Skipping to 17 to 15 million years ago as the North American Plate continued its slow journey to the northwest, it passed over a volcanologically active area known as the Yellowstone Hotspot. As the hotspot shifted underneath the North American Plate, it erupted violently with basaltic flows. Less intense eruptions continued until about 6 million years ago, resulting in a large flood basalt province known as the Columbia River flood basalts, covering approximately 63,200 square miles of the Pacific Northwest in parts of Washington, Oregon, Idaho, California, and Nevada. About 4.5 million years after the flood basalts formed, the last ice age began with the Pleistocene epoch at around 2.6 million years ago to 11,700 years before present. At 11,700 years before present, the planet began to warm, causing glaciers to melt and begin breaking apart. The melting of the glaciers caused large amounts of water to be transferred into the atmosphere, forming clouds and later precipitation that would begin to accumulate in river valleys and lakes. The Clark Fork River, however, was blocked by the thick Purcell Trench lobe, causing rainfall to begin backing up behind it, forming Glacial Lake Missoula. Glacial Lake Missoula was a massive, multiple-armed lake that extended 200 miles east behind the Purcell Trench lobe, filling the Clark Fork River Valley. Looking at the picture to the right, we can see the extent of the coverage of Glacial Lake Missoula and the late geographical location of the Purcell Trench lobe, labeled here as Ice Dam. Reaching over 2,000 feet deep, the water of Glacial Lake Missoula began to buoy the Purcell Trench lobe, causing it to give way and release a massive flood. The water that filled Lake Missoula rushed out over the span of a couple days, spilling into Lake Pend Oreille and overfilling it almost instantaneously. From Lake Pend Oreille, the floodwater rushed down the Columbia River and spread across the landscape, turning south as it hit the Okanagan lobe of the glacier, continuing southward across eastern Washington, picking up sediment until it met the Wallula Gap, where the flow was stopped completely. The removal of soils and sediment by the Missoula floods had extensively exposed the Columbia River flood basalts, the extent of which is illustrated here as well. Continual glacial flooding created a slack water pool behind Wallula Gap. Eventually, the sediment picked up by the floodwaters began to settle, and the water funneled through the gap and down the Columbia River. Over time, sediment began to accumulate on the riverbanks of the Columbia River, where marine polar air masses moving inland from the Pacific Ocean dried it into silt and carried it east, depositing it across the Palouse region of eastern Washington. The geologic origins of Kamiak Butte can be traced back to Precambrian time, with the uplift and compression of the seafloor around 100 to 50 million years ago during the delivery and accretion of Superterrane 1. Ancient sedimentary sands on the seafloor were compressed with the accretion of the superterrane, forming sandstone that would eventually become quartzite from surface warping, compression, heat, and time. During the eruptions of the Yellowstone hotspot, only the highest quartzite peaks, Steptoe and Kamiak Buttes, were able to remain above the basaltic flows of the Columbia River flood basalts. Following the Missoula floods, the Palouse was overtopped with a layer of loess soil, including Kamiak Butte. The soils of Kamiak Butte are nutrient-rich, but allow water to percolate away from plant roots as there is no impermeable layer of basaltic rock to prevent water from seeping away, like there is across the rest of the Palouse. As a result, only deep-rooted plants can grow successfully on the slopes of Kamiak Butte. Overall, these three major events, the accretion of exotic superterranes to the North American tectonic plate, the creation of the Columbia River flood basalt group, and the glacial Lake Missoula floods, played a huge role in the formation and geology of Kamiak Butte. Climate is defined as a combination of both precipitation and temperature regimes in a region over time. North America, in addition to other continents, is divided into macroclimates that encompass a broad range of climatic conditions within a region of the continent. Kamiak Butte lies within the marine-modified continental macroclimate, a large region of the North American continent that is overall temperate in climate and largely influenced by continentality. The elevation of Kamiak Butte also influences its climate. The slope of Kamiak Butte, in combination with its position in the northern hemisphere, results in solar radiation hitting the surface of the southern slope almost perpendicularly. This direct exposure to the sun greatly increases the surface temperature of the slope and creates droughty conditions that limit vegetative growth. The northern slope, on the other hand, faces away from direct solar insolation and is mostly heated by the reflection of solar radiation off of other surfaces. Lastly, the climate of Kamiak Butte is influenced by the movement of air masses. Marine polar air systems approach Kamiak Butte from over the Cascade Mountain Range and combine with high wind systems up from the Columbia River Gorge, supplying Kamiak Butte with ample precipitation and winds. Like climate, the biome of Kamiak Butte is influenced by its physical characteristics. Kamiak Butte lies within the western interior shrublands and woodlands biome, which is characterized by a temperate climate, shrubland or woodland physiognomy, and sandy or gravelly substrate. To the left is a picture of the characteristic western interior shrublands and woodlands biome physiognomy in Utah. To the right is the physiognomy of the natural vegetation of the Palouse. Kamiak Butte itself is a variation of the western interior shrublands and woodlands biome. This variation is due to the topography and angle of solar insolation at Kamiak Butte. As mentioned previously, the slopes of Kamiak Butte do not receive the same amount of solar insolation, with the south aspect receiving more radiation than the north. This results in only drought and shade-tolerant vegetation growing on the south aspect, and more shade-tolerant and drought-intolerant vegetation on the north aspect. Overall, more vegetation is able to grow on the north aspect of Kamiak Butte than the south aspect. A variety of wildlife inhabit the slopes of Kamiak Butte, including birds, ungulates, rodents, and canines. These wildlife interact with each other and the environment to create a unique ecosystem within the Palouse. In order to better understand these interactions, wildlife cameras were established on each aspect of Kamiak Butte. Ungulates, such as deer, moose, and elk, have been documented to walk about the slopes of Kamiak Butte in search of food or a mate. Since their removal from Washington state in the 1930s, wolves are no longer present on the slopes of Kamiak Butte. As a result, the populations of ungulates at Kamiak Butte has risen significantly and their consumption of vegetation is greater. This increases the amount of competition between ungulates, birds, and other mammals for forage. With some wildlife not being able to find enough food to sustain themselves, the populations of prey for predators like the coyote, red-tailed hawk, and Swainson's hawk begin to decline. This, however, does not mean that the ecosystem of Kamiak Butte is not healthy or stable. It merely indicates that the ecosystem is changing in response to the removal of a keystone predator, the wolf. Kamiak Butte also provides a safe habitat for wildlife within the Palouse. Since the 1820s, the Palouse region of eastern Washington has been heavily converted to agricultural farm and rangelands, significantly reducing the amount of natural vegetation in the Palouse. Today, less than 1% of the natural vegetation remains within the Palouse Prairie. As a result, Kamiak Butte provides a safe habitat for wildlife seeking refuge from the disturbance of the Palouse region, especially since its designation as a National Natural Landmark in 1965. Wildfires are naturally occurring events that can improve the overall health of a forest ecosystem by returning nutrients trapped in dead and dying organisms, as well as opening the forest for the establishment of new vegetation. However, if a wildfire were to occur at Kamiak Butte, what would happen to the wildlife? Though it may not be as evident, the occurrence of wildfires can potentially benefit the wildlife of an ecosystem. If a wildfire were to occur at Kamiak Butte, it would burn at a low to moderate severity, as most of the vegetation at Kamiak Butte has a medium to high fire tolerance. The response of wildlife to wildfires can be grouped into two general categories: birds and mammals. Birds are mostly affected by the severity of the fire and which season the fire occurs. A low to moderate severity wildfire can injure or kill young birds nesting on the ground and understory, but not birds in the canopy. However, high-severity understory fires and crown fires can. The proportion of birds that are injured or killed becomes greater during nesting season, as nestlings and fledglings are unable to escape. Mammals, on the other hand, are affected depending on their mobility and the size, severity, and uniformity of the wildfire. Small mammals, such as squirrels and chipmunks, tend to relocate within the burn in underground burrows or sheltered places, whereas large mammals, like deer and elk, tend to search for unburned locations. Mammals that nest on the ground are more vulnerable to injury and mortality. Post-fire, many birds and mammals return to the ecosystem within hours or days. Other animals may choose not to return, as the required food and shelter are no longer available within the ecosystem. Some wildlife, however, are attracted to post-fire ecosystems, as they may provide more abundant and exposed food. Mammals are often attracted to the new growth of vegetation months post-fire. Overall, if a wildfire were to occur at Kamiak Butte, both the forest and wildlife would benefit from the post-fire ecosystem. To conclude, Kamiak Butte is a unique ecosystem situated within the Palouse region of eastern Washington. It provides not only a refuge for wildlife, but a place for students like myself to learn the wonders and importance of ecology. If you ever find yourself in Whitman County, Washington, I suggest that you visit Kamiak Butte. Thank you for watching.